So recording I have started. So the plan today to have a lab. And the lab have 1 week, or actually more than 1 week. You need to submit it back by, I believe, 26. Not this coming Friday or Saturday, the other Saturday. So you have 1 week and some days. For today, we'll discuss first of all, what are the corrections? So we start, I think this is where we have left last time. So we'll talk about corrections and what we do, type of corrections on gravity data and why we do these corrections. The data we record initially, they are still in raw format, in a format that are not representative of the physical properties of the Earth. So welcome everybody again. I'm seeing more students are joining. That's a good sign. Come in. Alaikum salam. I repeat what I said. So for today, we try to cover a few slides before we go to the lab, because the lab is about how we do corrections. I have a recorded video of previous years and the other year as well, or previous semester, the same lab. It's the same lab, I'm repeating it again, but it's a very important lab. I believe you need to do it as well. How to do gravity corrections. Recently, few students went to Qatar. They just graduated. Some of them, they were actually geologists. They were employed by a company doing geophysical surveys. They got a big project in Qatar. They stayed there for 3 months. They contacted back. They recently get back here. One of them, they joined them since graduation because the situation is intense. The oil prices, at least the last year, was very low. Job market wasn't that promising. Many students, they left without jobs. But things are getting better and better, especially for geologists, geophysicists, petroleum engineers. They worked a lot in gravity analysis. The task was doing a gravity survey, detailed gravity survey of some area there. You know, the construction field or construction sector back in Qatar is really, really booming, and they need a lot of surveys, gravity surveys, what type of soil can support skyscrapers, long-story buildings. And the gravity technique is one of the methods which can help you decide whether the construction site, is it safe or not. So today we'll talk about how we correct the data. The data, as I said, we give them in a raw format. Some of the information contained in the data, they are non-geological. Whether the others are geological, we need to remove the non-geological part and only keep the response which is coming from down the ground. So first of all, if I say the corrections, the first corrections comes to us is drift, then latitude correction. Drift means drifting and moving from the one baseline probably. So there is a drift correction. The second one is latitude correction. Latitude is خط الطول ولا العرض؟ Yes. خط العرض. So what's the longest or largest latitude and the smallest latitude? Lowest latitude. What is the smallest latitude? One can go there. Minus 90. Oh, come on. What is the largest latitude? 90. South Pole and North Pole. Equator is, what latitude is it? 0. So this is the basic information. Then comes ETVOS corrections. ETVOS correction, it's not necessary correction. It's done whenever I'm taking measurement while I'm in a moving vehicle, whether it's a car or a drone or an airplane. So it's, or even a ship. Topographic correction is another correction. We do a lot of corrections in topography, so measuring elevation of points is very important. And whenever we do elevation points, the handheld GPS are not sufficient. They don't give you precise information of elevation. Nowadays, even phones, they give you information. They have GPS, am I right? Every phone, smartphones nowadays, they have GPS. It's actually, they provide usually somehow precise XY location, coordinates, easting and northing are good, whereas the most difficult to measure is elevation. There are a lot of errors in elevation measurements. Even the handheld GPS, they are not that much precise. The error within them is almost like 10 meters, 50 meters. We use some kind of GPS, we call them differential GPS. Walaikum salam. So the attendance sheet actually is passing by. Don't forget to write down your name. So we need to record the data itself and an additional information, which is the coordinate, x, y. Whenever I talk about coordinate, I'm referring to three different information, x, y, and z. Those corrections comes under topographic corrections. They are considered or categorized are Fourier correction, Bouquet correction, and terrain correction. Final correction, which is not necessary, we call it residual correction. So let's go along them one by one. First of all, there is a correction called drift. The last time we discussed the type of instrument we can use to record gravity data. Graphimeter itself consists of spring. Consists of what? A spring. What is the paradox? What is the parameter that controls the force spring? How I can easily or hardly stretch a spring? M times the M, my force, probably M times spring constants, K. Spring constants. Some springs are easy to stretch, others are tough. And the determining factor is the spring constant. So we know that parameter, spring constant, is not actually very constant. It's somehow constant, but can get affected by either temperature or even time. Temperature, pressure, they affect the spring constant. It varies in the same day, at the same location. So if I'm recording using a system that depends on a spring, I expect that at the same point, geological point, there might be variations. Those variations are not related to the geology, whereas they are related to change in temperature and pressure probably. And the best thing to avoid them actually to isolate the spring. The system itself, the graphimeter is isolated. It's kept in a place that's to minimize the effect of temperature and pressure as well. Anyway, there is a drift. There is a drift. There could be a drift. The drift is basically spring creep. Spring getting creeped. The spring constant is changing through time. How much it's changing? It depends on many factors. We don't go to the details, not necessarily. So drift could be for two reasons. One of them is a spring creep. The other one is, we do this drift correction for two reasons. One is diurnal corrections, diurnal variations. The other is because of tides. The other is tides. We know that there is a force between the moon and the earth, moon and the sun. The maximum force on the moon will be, when will the maximum pull you think will be? When the moon and sun are aligned in one side. They pull the earth together. They pull. So people on one side in the same line, they will feel a lot of pull toward the moon. The people on the other side of the earth, they feel they are pushed against the earth. So if you want to be very long person, be in a flight and the plight in the orientation where the moon is. So you are always where the moon is, full moon. You might get longer. That's how they say. So these two variations, they are not of geological interest to us. They are external factors. We need to remove them. One way to remove them, and the actually basic way, the fundamental way to remove them is if there is something changing in the same location, how I can record the change? What's the easiest, simplest way to record the change? The same point. Change of any measurements, like tidal effects. Huh? Repeat measurements. The geology, do you think the geology would change through time? In 1 day, 2 days, or 1 week, 1 year, 3 years? Geology changes in terms of millions of years. So the basic way to remove the diurnal correction is periodically returning to some reference point. That reference point, we call it base station. A point we go back. And that's the reason actually I'm doing relative gravity measurements, not absolute measurements. My measurement relative to some station established in the field. I call it base station. I go back, visit the point, keep recording. I need to record two things. First of all, the reading itself, the other parameter is tick, 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 is time. I need to record the time as well. At what time I recorded the data. So those two parameters are very essentials. So we will subtract. The first time I recorded, the second time I recorded, if there is a change, it's certainly because that there is either a creep, the stiff constant of the spring is changing, or there is tide effects. I need to remove these two parameters or these two changes from geological reasonings. I basically go repeat the measurement in the base stations. In the station I take as a reference point. So if I assume that I removed every other parameters and this is a change due to time, I assume that this is change due to time. This is all the recording. It includes time change and some geologic change at many readings. Whereas in the base station, I see some change like that, repeating change throughout the day. Those changes are due to what? Tides. Repetitive changes are due to tides. I simply subtract this from this, I get some anomaly probably. It's not that simple. We'll do that in our exercise. The raw data represents the reading at a lot of points, another reference point. You are going distance, one point, another point, so on. Other points you are surveying in the area. It's a bit hot, I believe. Don't have control here, anyway. Whereas this is the readings at the base station. I remove these readings considering the time range. I remove them from the other readings, the readings I have taken other points. I get a good anomaly. The other correction is latitudinal correction, the change due to change in or change in the little g due to change in the latitude you are taking measurements on. We know that the Earth is not a perfect sphere, it's actually a bulge. It's what? A bulge. It's thicker in the poles than the equator. Am I right? No, it's thicker in the equator. It's thinner in the pool. So the equator, that's how is it? The velocity itself, the little g, the average g value, gravitational force at the equator is 9.78, whereas the average gravitational force at the poles is 9.8. The determining factor is basically R. It's R. And that's happening because of the centrifugal force of the Earth. It is revolving around itself, and it's trying to throw its internal material away. And we know the centrifugal force is in opposite direction to the gravity force. The direction of the centrifugal force is in the opposite direction. It's similar if I rotate quickly or revolve quickly along myself, and if I'm holding something in my hand, I stretch my hand, of a sudden, what happens to the object I have? It will be thrown away. It will not come toward me, but it will be thrown away. That's what I say centrifugal force. If it's in the center, if it's exactly on top of my, can stay, will not fall. That's the same force. So this force is actually changing the shape of the Earth. The centrifugal force makes the Earth flatter at the equator than the poles. So the radius of the Earth is different. Oops, sorry. The radius of the Earth at the equator is how much? 6,378. Well, it's smaller in the poles. So we know the gravity force depends on the R, the radius to the Earth. That's the gravity force, overall gravity force. So there is a change in gravity, overall change in gravity. And that change is basically can be represented as such. So at 0 we get lowest. At 0 equator, because we say the gravity force is lowest where at equator. It's highest at the pole, South Pole or North Pole. And it's depending actually on this equation. You don't need to derive the equation, you need just to use the equation, how to use it. It's in milligal, that unit in milligal. Could be gravity unit. But what is the important parameter in here? What you need to change? You need to change what? Lambda. What is lambda or theta? Theta could be minus, maximum value of minus or plus 90, and the minimum value is 0. Minimum value is 0. So sine of 0. Sine of 0? 0, am I right? Yes. Sine of 1. 1. Square of it is 1, 2. So maximum value, you will get it at either North Pole or South Pole. It's simple, and the corrections, the maximum correction you get is almost 0.8 milligal per kilometer. Each kilometer you go either up or down from the reference point or reference line, 0, equator line, you will add up 0.8 milligal for every kilometer. So speaking of meters, how much meters? It's almost like 0.001. And we need a good equipment that can measure even one change in meter. If my equipment is having that much accuracy, that's the accuracy. If anything smaller than that, I cannot record it. That's the dynamic range of my equipment. When I say dynamic range, I mean what is the maximum value and the minimum value something can record. Any equipment in the world has a dynamic range. You know that, am I right? And dynamic range, what's the smallest value and the largest value something can record. Some equipment, they can't record very, very high numbers. They can't even record very, very low numbers. And the dynamic range is the ratio of high to low. That's the dynamic range of any equipment. That's also, we call it sensitivity sometimes, how sensitive these instruments are. So usually the graphimeters, they can record up until that much change. If the change is lower than that value, they cannot record it. If there is a change smaller than this, you might not be able to record it. You need probably a better instrument than, more sensitive instruments. Considering this sensitivity, if that's the sensitivity and that's the change usually per kilometer, you can record change if you move 12 milligal. Yani there will be 0.02 or 0 plus 0. You add that much value for each 12 meters you move. So if you are moving 4 meters, 1 meter, it's negligible. That error is negligible. So if I'm moving up, what happens to the gravity value? It increases. And at the poles, the gravity value is largest. So if my reference point, this is my reference point at the 0 equator, I moved up. And there is no change in geology. And I removed every other error. Only latitude correction. Would I get higher gravity value or lower gravity value? Higher. So I need to subtract that value. I need to subtract it. If I move down, I need to, if I'm moving also down, I need what? Below equator, I need to subtract it. If I'm moving from poles to equator, then I need to add it. I need to add it. That's how it works. So dependent on where are you moving? Are you moving up or down from your base station? So that was the what we call latitude correction, simple correction, easy correction. It follows this long equation. You don't need to change anything. The input parameter is only latitude. You change the latitude. So that's the latitude, sine of latitude, squared sine of latitude. Then it comes to the ETVOS corrections. If I'm on the North Pole, I know the Earth is rotating. If I'm on the North Pole, would the Earth be rotating clockwise with respect to me or anti-clockwise? Clockwise. Who says clockwise? Who says anti-clockwise? Let's say if I'm in Muscat, I went to west, to London. Did I add time or lose time? Huh? Add time? Now you lose time. If you go to east, if you're London, you come يعني انت طلعت من هناك الساعة 4 مثلا العصر، ترجع هني كم الساعة 5 بعدها، وخذ منك 8 ساعات. تجيت هني كم الساعة كم؟ الساعة 5 أو الساعة معه. لكن إذا مشيت العكس الساعة 4 العصر ما ياخذ منك يمكن الوقت 7 أو 8 ساعات، وصلت هناك ثاني يوم كأنه واصل. أنت ضيعت من حياتك يوم راح من حياتك كأنه وأنت في الطائرة، بدل ما 8 ساعات المفروض تخسر 8 ساعات بس، ما صح؟ يعني توصل هناك إذا 4 طلعت، خلينا نقول كم ساعة كم توصل هناك؟ 12. لا بتوصل ثاني يوم. That's how is it. So let's say if I'm moving, the Earth, as we said, is moving counterclockwise. Counterclockwise. So if you move against the Earth, if you move against it clockwise, you're counter-attacking which force? Gravity force or centrifugal force? Centrifugal force. Your weight will be, you will feel more weight. The gravity force will increase if you're moving clockwise. If you're moving to the west. كنا أنا رايح لندن واركب الوزن يكون أثقل علي لأن أنا ماشي عكس centrifugal force. Centrifugal is trying to throw me away, decrease my weight. So that's how is it. There is a loss of gravity if you move counterclockwise. If you move counterclockwise, same rotation as the Earth rotation, you are adding to the centrifugal force. You are adding to the centrifugal force. Your weight going to be even lower. The G will be even lower. And this is all depends on this equation. That's equation. So it's made of two terms. First parameter, that's the one. The other one, these parameters, it's Fermi-Legal. So that's V is the velocity. Theta is what? Sine alpha not theta, alpha, the angle you are moving with respect to the azimuth, with respect to the north. So the minimum is, alpha is 0 if you are moving exactly north, and the maximum is 360. 360 and 0 are the same. Am I right? So sine 360, how much is it? 0. Sine 0 is 0. All of this will cancel. If you are moving up or down, exactly. Sine 180, how much is it? 0 also. Sine 90, 1. Sine 270, minus 1. So this is going to be maximum if you are exactly moving south or east. Yeah, either it's maximum in terms of value, absolute value. It's going to be minimum if you move west. تتحرك 270 بالنسبة للأرض كلمة west ما صح؟ If I'm moving west, this is going to be the minimum. This it was correction, all of this is going to be minus, negative value. Anything from 0 to 180, it's positive. Plus this parameter. Again, V is what? Your speed. V is speed in kilometer per hour. Another parameter is cos alpha. So let's assume I'm moving 90 degree. I'm moving 90. I'm moving to the east actually with some number, speed number. And at which latitude you think this is going to be largest or smallest? Cos 90, how much is it? Cos 90. Yeah. Cos means that at poles it's the lowest. At equator it's the highest. At equator it's highest. Either you're highest in terms of absolute value. Either you're moving right or left. You're moving left to the west, it means you are decreasing. This is going to be minus. This term going to be minus. This is also dependent. Would it ever be 0? If there is a movement, would it ever be 0? No, because this parameter here, very small parameter, this can't be 0. If there is any velocity, this cannot be 0. Overall, for every kilometer per hour, if I'm moving 1 kilometer per hour, the maximum change is almost 2.5 milligal. That's large. The smallest number an equipment can record is how much? What's 0.01? So this is large. For every 1 kilometer, when you press your speedometer, gas, it goes so fast. You cannot record how much increase was. The acceleration is large. And that's actually a reason that airborne gravity surveying are not so accurate. That's a limiting factor in airborne gravity survey. This correction is the largest correction usually, adverse correction. Usually anomaly you observe is less than 2.5. The change or the anomaly is probably 1.1, 1 point something, whereas for every kilometer you are adding or removing 2.5 milligal. That's a large. So if I'm moving 20 kilometer hour, I multiply this number by 20. If I'm moving 100 kilometer per hour, wow, that's going to be a very large number then. That's going to be a very, very large number. And that's actually a limiting factor in gravity surveys. Then we move to topographic corrections. Topographic corrections are applied because I'm either moving up, down, one of the reasons. The other reason is because there is an extra weight or extra mountains with respect to the reference point. So let's take some examples. This is the example I have, simple schematic diagram showing my recording or survey configurations. That's the reference base station. A is the reference base station. Let's assume my next point is point B. I moved up by some distance. What happens to I moved up by some distance. What happens to the gravity value? It will increase? Huh? What do you think if I move up? It will decrease. That's for certainty it will decrease because the R, what happens to the R distance? Increases. So that's what happens. This is your base station. So if you move up vertically, I think that the geology beneath this point B is not changing. I'm still in the same XY location. Z have changed. So there is a decrease. If I move down below reference point A, what happens? It will increase. I came closer to the Earth center. R decreased. By the way, what do you think is the gravity value at the center of the Earth? If you, What's the gravity value? If someone is where exactly at the center of the Earth? It's zero, yani. It's because, It's R is zero. That's one reason. But mathematically, R is zero, error. Yeah, if you put the calculator will not give you an answer. It's then a complex number probably. But the reason being because you are at the center, you get forces from all directions, and they are equal forces. They're equal. The force from this direction, all the directions are equal. So you get zero force. The gravity force is zero. You'll be floating as an instrument. Yes?
If you go a little bit farther away from the source, isn't the gravity very high?
If you move away from the source, as we defined the gravity equation, it is dependent on the distance. So distance increased, and we know that the relationship between the force and distance is inverse relationship. They're inversely proportional to each other. It means if distance increases, what happens to the gravity? Decreases.
But then if you're very, very close to the source.
It's very high then.
It's very high, and then all of a sudden it goes to zero when you're in the center.
Yes. In the center, the forces are all almost the same.
So it's like there's like a discontinuity.
So if, let's say, if I take the Earth, that's the hole. If I drill a well through there, and I ask you to jump in this hole, you will fall. You will fall right away. When you arrive here, your force is so high, you're falling with a high gravity, you will not right away stop. What happens to you? You continue. And your force is decreasing until you reach this point. يعني الاكسلريشن صار صفر. مرة ثانية ترجع. كأنه pendulum. Ting, 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 ting. Forever. Assuming that there is no other external forces. Only gravity, and the Earth is not rotating along that. It's rotating only along itself. Or it's stationary. ما في فورس ثاني وانت نزلت. بداية الاكسلريشن صفر. جرافيتي في جرافيتي، لكن الاكسلريشن مالك يبدا بصفر. ما صح؟ يبدا يزيد يوصل هنا يبدا ينقص. And it's cancelling out until you reach this point. You will not stop here. You will go through it until you reach this point. It's again getting zero.
What is this degrees with the my acceleration?
Sorry?
Before I reached the core, you said that.
It increases as you go here. It increases. Even here exactly it's zero. But there is an inertia. You are already moving, and there is no force that will stop you. If someone stops you, you get shattered into small pieces. Yes, you get shattered into really small pieces.
So how come I'm still moving, but the acceleration is zero?
The acceleration, the force are there zero. Your momentum is not zero. There is a momentum you have. يعني إذا شت كرة، الكرة تتحرك تبدأ تخف، ما صح؟ فتسألني ليش الكرة تتحرك ما في فورس عليه؟ الفورس كان موجود من الأول. I shot the ball. That's the idea. Anyway, this is beyond our course. So again, there is other corrections we need to apply. Free air. That's correction actually if you go up and down, considering that there is no change in rocks. The Earth is flat. If we move up and down, that's called free air correction. That's the reason they call it free air. It means that there is only free air. There is no rock. I moved up. There is a free air correction. And the value of that correction is that much, milligal per meter. It's way smaller than actually latitude correction. It was correction. It's way smaller than it was, but it's larger than latitude correction. This correction is larger than latitude. For every meters, approximately 0.3086 milligal per meter. So if I move up, should I add that if I move up? That's my point A. If I moved up by 1 meter, should I add that much value or decrease or remove, subtract? Should I add it to my reading or remove it? If I'm moving up, add. Who says add? Who says remove? You add it, come on. Because the gravity is decreasing. It's decreasing because I moved up. The geology is beneath me is the same. It decreased. So I need to add that much. And not necessarily always, in any case, only in this specific case. If I move up, that's my initial point, beneath me exactly, I move up, there is a decrease in gravity because I moved away from the center, I moved away from the measurement point, the R increased, I need to subtract that value. So if you move, let's say I moved 50 meters, how much is the correction value? If I move 50 meters, 50 times this value, that's true. Simple calculation. That's one correction. This is the correction we call free air correction. easy, simple. So this is the free air correction. You don't need to know about. So it's positive if H is positive. It's more than 0, greater than 0 if you are above the reference point. If you are below reference point, it's negative. You need to subtract it. And if I move closer to the Earth center, what happens to the gravity value? It increases. It hasn't increased because subsurface geology has changed. It increased because just I moved into deeper, closer location to the Earth radius or Earth center. The radius of the Earth decreased. So it's negative. In such cases, you remove. In such cases, you add per how much kilometer? H times that value. H times that value. The correction value. So that was what we call free air correction. There is another correction, we call it Bouquet Correction. Now,
Do we need to do topographic correction before we do the free air correction?
I said topographic. That's a good question. I said topographic correction. Topographic correction is a collective correction of different things. One of them is free air. The second one is Bouquet. They are all topographic correction, change in topography. So one of them is free air. The second one is Bouquet correction. We will just tackle right now. There is another correction called terrain correction. 3 different corrections in Bouquet topographic corrections. We correct for all of them, 3 of them, we call it complete topographic correction. That's the point I was soon coming to. So here is the point. That was my initial point, base station or reference point. That's the point. I ask, what's your name? Khalil. Remove Al, make it my Khalil. So let's say that this is my point, initial point. How I do drift correction? How drift correction is done? How I do drift correction? If this is my point. I took measurement here, then here, then here. What I should do? Huh? Sorry? No, you come back. After some time, what you do? You come back and take measurement here. We repeat measurements where? The reference points. That's how the drift correction is done. The drift correction, this is how it's done. You return back to the base station. You keep returning back to the base stations. So by the way, the gravity equipment we have, it's called CG5. It's CG5. The new version is CG6. Once I did a survey, it was the first time I'm doing gravity survey. I switched on the equipment when I arrived there. I started acquisition, I switched, and I was surprised that all the readings are the same. All my readings were the same. There was no change. Very slight change. Even though there is huge topographic and other changes. Yes, within like 4 or 5 hours. Then I was surprised. I said, no, I should stop. I don't waste my time. There is something wrong. What do you think is the wrong thing? It's hard to tell, but our instrument, we need to switch it on before we go to we need to warm it up. It's an old car. سيارة القديمة ايش لازم تسخنهم قبل ما تتحرك. أنا دائما من أطلع من بيت أبويا أشغل سيارة أبوي لحظة خلي السيارة تسخن شوي ليش مستعجل؟ Yeah, the old car, but new cars, it's fine. You just switch it and let it go. Press the gas. So that was happened. You need to keep it warming up. Switch it on, keep it warming up, then you go to the field, acquire data. That was how the drift correction is. Let's assume that I have taken right now a measurement at this point, point C. This was the reference line, datum line. This is because I established the base station here. I move the point C. What do you see? What's that? Do you see this line? This is what? A mountain. That's a mountain. This is a mountain. So what do you think mountain will do to the gravity? If there is a mountain, I'm interested in something below here, deep here, below point A, basically. What happens because I move to point C? What happens to the gravity? It decreases for one reason. It increases for another reason. The other reason because there is extra mass. There is an extra mass. It decreases because I moved up. It decreases because I moved up. That's free air. Free air, I moved to this level. So I need to apply free air. It increases because there is also extra mass, a mass which is not of interest to me. Then we need to apply what we call Bouquet correction. And how it's done? It's almost like when we have an infinite sheet. Do you remember? We have an infinite sheet. The gravity correction will either add a value or subtract a value depending on the density and thickness of the slab, of the infinite layer or slab. Similar correction. So if I go back, shall I? Just don't waste time. Let's keep our focus here. Free air correction, then we go to Bouquet correction. Oh, let me show it very quickly. Just a reminder. That's how is it. You see? That's an infinite slab. It depends on two things. The density of this layer and also T is what? Thickness of the slab. It's just so hot here. Yeah, any questions?
Yes, about the mass here. If they are different types of the lithodology, like the granite, so that will be affected to the gravity or not?
That's true. It will affect the gravity. Yeah. The question is, he asked, what about if there is not one single rock? There are many different rocks. Would it affect? Yep. If your rocks are below, if your target is below the reference points, and that's what you are trying to get, what are different rock types? That's finally your objective. Those are the variations you want to achieve or obtain or record. If those variations, because they are different rocks, different densities, yes, you will get basically different bouquet or anomalies. So here I do what I call Bouquet correction, and that's the same thing. You see, you have seen this one, 2 pi g density times elevation or thickness in this case, thickness of this slab. We assume it's made of infinite slab. This is just a unit. That's the value. This is exactly same to the slide previous slide I showed to you. 2 pi g times density of this slab, times the thickness of the slab. And it turns out to be that much per milligal. If I calculate it per milligal, I need to know two things. For free air correction, I need how many parameters? Which is what? Elevation. In this thing, in this correction, for Bouquet correction, I need two different parameters. One of them is density of this rock. The other parameter is the elevation. This is the same elevation we use for free air correction. This is the value. I give you these values. I give you the number without the equations, probably. So for the exams. So this is how the value. What's the value we use? Milligal. Per how much? Per meter. Milligal per meter. Every meter you move up and down. So one might ask, okay, we know H. H is basically the reference or the elevation from the plane, from base station. What about density? From where we get it? Huh? Yeah, the density from crust. That's. Did you read? Do you have good hockey, observation hockey? Do you watch One Piece? So that's actually true. We get the average density of the crust, which is almost like 2.7, 2.5. So we can assume this one as 2.7. That's the average density of the crust. It's not an accurate way, but yeah, for common survey, that's fine. And the best way, if you have a good tool that can measure densities of rocks, you can measure the density of the rock. One way of measuring the density of rock, weight it, bring it to the lab, sample of rock, bring it to the lab, and you can calculate what its density, provided you know its volume. Yeah. You need to calculate its weight, then its volume, then you can work out what's its density. So that's how is it. What about the value? Shall we subtract or add this value from the base? Shall we add or remove? Remove. That's true. We remove, subtract this value. This is an extra rock that's not of interest probably to us. We are looking at things below the base station. So if he or she asks you, where should I place the base station? What is the best consideration? First of all, you need to place it somewhere which is very accessible. Easily you return back. Don't put it far away at one end of your survey. Put it in the middle of the survey, because you need to return back a lot to the base station. Is that good? So we need to remove this value. But we need to remove it if we are doing onshore surveys, land surveys. If we are doing marine surveys, so that's the value, 2.67. That's the density, average density. If we don't know it, we assume it's the density of average density of the crust, as some of you say. That's the value. So if we multiply that value, we'll get this value is 0.112 times the density, times the thickness, or times the elevation from the base station. If you are in marine, offshore survey, marine survey, what is the average density of the rock? What's the average density of water in gram per cc? 1. But marine or seawater has some salinity, so its density is a bit larger than 1. So we subtract density of marine, that value, density of gas, subtracted from density of water, seawater. That's going to be the value of density. It's minus, negative value. So that's how is it. This is going to be added. If you are doing marine survey, you add that value to your reading. You add that value to your reading, reference to the base station. Again, I'm always saying reference to what? Reference to what? Base station. Because we are doing what type of measurement, gravity measurement? Is it absolute or relative? Who was that? Huh? غلطان? Anyway. So this is what we call Bouquet correction. This is Bouquet correction. We have Bouquet correction, that's the value of Bouquet correction. Free air correction, together we call them elevation correction. Bouquet correction, free air correction, if we are above the reference point, it's positive, we add it. In land onshore surveys, we subtract Bouquet correction. That's the elevation. Collectively, it's called elevation correction or combined elevation correction. So then things are still getting more complex. I go to a point called D. So I don't have only something below me, I have something pushing me toward itself, a mountain. And there I have also, what's that? Huh? What? A valley, wadi. That's a valley, this is a mountain. They're trying to cancel off each other. Here we need to do terrain correction. This is a terrain correction. And terrain correction is done through a plot. It's a bit difficult, it's not easy. So we'll not tackle the problem here. We will not go in detail how exactly it's done. Students who will take the other course, gravity and magnetic methods, will study in detail how they use a chart that can help to determine what is terrain correction. But one parameter which is not easy to bring in order to correct for terrain is to get elevation points. يعني I need to have elevation points not where I take measurements. I also need to get elevation points in every probably 50 meters, right to left. I need elevation point covering all my survey area in a graded way, 50 meter, every 50 meter in the X direction and Y direction. I need to get elevation information, which is quite complex, and it will add a lot to your budget, the cost you need to be ready to spend on the survey. يعني مثلا الحين شركة جاية من الأسبوع الماضي لو عندي خليل نريد نسوي جرافيتي ونريد نستخدم differential GPS. نريد نسوي we need to do terrain correction. I said it will cost you, it will add double the price. يعني الجرافيتي سيرفي بنفسه يمكن يكلفهم 3000، هذا السيرفي بيكلفهم بعد 3000 عشان نحصل الاليفيشنز، ما نقطة واحدة، أكثر من نقطة. نقاط كل 50 متر يمين يسار. I need to get elevation value XYZ precisely to do this correction, terrain correction. So if you think that there is not a lot of topographic variations, the area is flat, it's a plain, is it necessary then to do terrain correction or not? No, don't do it. Don't waste time. Don't do it. If you have someone who already made an accurate elevation map of the area, then use it. If you have it available, just use it. So in case if I'm doing survey in Batna area, which is a plain, would it be necessary to do terrain correction? No. However, you are doing a correction, let's say in Bidbid, which is a mountainous area, there you need to do terrain correction. Because you might be at a point where it's stiff cliff between the point, measurement point and the mountain. There you need to do terrain correction. It's a must. Otherwise your measurements are just a junk of errors, wasteful of time. So this is the terrain, the last correction. And as I said, it's good to do it if there is erratic change within less than 200 meters. That's a rule of thumb. If there is high topographic variations within 20 meters, then do it. Otherwise, it's not necessary. So that's the total correction. We need the measured data. We think that we applied, first of within the measured data, we applied the first correction, which is what? What's the first correction usually we apply before anything? Huh? Drift, that's true. So first correction is drift. Drift is done by going back every 1 hour or every 2 hours to where? To the base station. We go to the base, visit back base station. The next correction is latitude. If you are going to the poles, either north or south, you need to subtract it. If you are already in the pool and you are moving to the equator, you need to add it. Then we have free air correction. What's the sign of this correction? Sign. يعني موجة ولا plus? Positive. That's a positive. Why? Because if I move up, I add. If I move down from the reference point, I subtract. Then comes what? Bouquet correction. I assume that there is a long slab of rock between the measurement, the base station, and the measurement points. Then I remove it. I subtract that value. Then terrain correction. Then I apply terrain correction. Terrain correction could be plus, could be negative. Depends on the type of correction or how you are doing it. And one of the corrections which is not very necessary, it's only necessary if I'm moving and in a moving vehicle. So that's the correction. The important thing is there, what? If I do terrain correction, I name my final correction complete. This is Bouquet anomaly. Applying all corrections, it's called Bouquet anomaly. So don't confuse between Bouquet anomaly and they are two different things. Bouquet anomaly and Bouquet corrections are totally two different things. This is a correction, whereas this is the result of applying different corrections. If we go back to the first chapter, what we consider these things? Processing or modeling or interpretation or reduction or acquisition? Reduction. What we are doing right now is data reduction. Data reduction. We are removing non-geological parameters from geological chains. So let me put this into the charger. You keep recording, it drains a lot of batteries. So final Bouquet anomaly we record, we assume that we removed any non-geological change. Whatever we are recording or the response we are getting is the response of density variation, geological variation. We are encountered with different rock types. That's the Bouquet anomaly. Again, if you apply terrain correction, we call it complete Bouquet anomaly. Without terrain correction, it's called simple Bouquet anomaly. So whether we are doing complete or simple, it depends, are we doing terrain correction or not. So these are the correction, all the corrections we do. One thing is missing is drift correction. Drift correction is very necessary. I will study later then magnetic methods, and magnetic methods actually, these corrections are not must. The most important is the diurnal correction. Diurnal correction. And that's the reason magnetic method is very, very popular. It's very popular in archaeological investigations and trying to find some old ornaments. It's very popular in metal detection, ore body detection, magnetic methods. So that's how is it. This is the total corrections. Finally, there is another correction, final correction. We said it's residual correction. It's residual correction. We try to remove original features from residual features. So what we are doing actually, for example, let's assume this is the model. That's the Earth model. Here I have an ore body. It's a metal probably, iron ore body, gold ore body. These are heavy metals, so you expect that the density of the material is going to be large. This is the basement. Basements are usually non-sedimentary rocks. Below the sedimentary rocks, we see the basement. This is the basin rock. A basin is a bowl where sedimentary rocks get deposited. Below the basin is the basement. Basements are either igneous or metamorphic rocks. In Oman, where we can see the basement rocks? In Wadi Hattat, in Sur we can see it, in Salalah we can see the basement rocks. The students will take the geology of Oman, they will study these things. So this is the basement. What do you think about the gravity? Will it be here larger due to the basement or here? Left or let me assume that I'm sitting in your place. Right or left? Where it's higher? Here? Huh? Left. Because the basement, which is denser, is closer. Denser material came closer. So the anomaly will be larger. Am I right? So what's the shape of this anomaly going to be? Is it going to be a zigzag line? What? A curve? A linear line. A line, straight line. Going to be a line. In here it's larger, in here it's smaller. That's how is it? That's from the basement itself. There are two responses. What about this body? What kind of anomaly you see? It's going to be something like curve. Like a bell shape. جرس مثل شكل الجرس. So here, if I take measurements and I assume that I'm starting from here. Remove this one and assume I'm starting from here. Am I right? So the lowest is here. What happens if I move to this direction? It will increase. So this point is there. That's something wrong. I should have put 500 here and 0 there. So it's lowest point here. I move to the left. The basement is coming closer. What if there is only this sediment? All of this model is one sediment. What do you see? Huh? What the value of the straight line is? 0. There is no anomaly. If I'm recording only the relative change, there is no change. Yeah, if I'm recording the absolute value, there is a straight line at some specific value, 9 point something, in terms of meter per second. In milligal, it's going to be large number. So here, it started increasing. I might assume that my base station is here. I'm referencing back to the base station. I'm going to the right. When I come to here, I see what? A bulge. That bulge is due to what? The ore body. So usually, as a geologist, what you are interested in? Huh? Are you interested in the what? Chrome, yes. This could be an ore body, a chromite. So, as geologists, you are interested on this thing. These are very deeply seated basement, very deep. I don't care about it, but still it's giving me a response. So I need to remove. Which one do you think, which of these is the residual and which one is the original field? Which produces, or what response is producing the original field? Is it the ore body original or the basement? Basement. Which produces the residual? The ore body. So one way, basic way, I'm not sure whether you are aware of filtering, 1D filtering, 2D filtering. For such thing, you do trend, D-trend. There is a trend, am I right? You see a trend, straight line almost, that's a trend. When I do D-trending, I pass a straight line, and I subtract my data from that line. That's D-trending. That's my trend. I plot a line which is covering the trend. I remove it from my data. So if this minus this gives me the green curve. That's what basically is residual to regional correction. I'm interested on this feature. I'm not interested actually on that regional scale trends. That's how is it. So here, for example, what you get by the end is this. That's your final anomaly. This is your final anomaly. But if you analyze it, you will find that there are two other different regional fields. One of them is this trending, then this ball shape, this valley shape or ball shape you see here, this deflection to the ground. So this small thing is produced from what? What do you think produced this bulge? Dike. Granite, we assume the granite is of lower density than the sedimentary layered rock, dipping rock. So it produces what anomaly? This anomaly. You see this anomaly? It's coming down up. The density of the granite is lower than the density of the sedimentary rocks or the basement, including the basement. And the dipping strata, they produce what? This regional field. That's due to the dipping strata. So if you are good in removing data or doing filtering, I ask something. Which of these features is of high frequency? Which is of highest frequency feature? Is it the dike, granite, or dipping strata? Huh? Highest frequency. Frequency is that, let's assume frequency is a lot of shaking. Small shaking is, what is the frequency, this line? 0. So the dike has the highest frequency. So if you are good in frequency, you do frequency filtering. Remove for me what they call low frequencies and keep high frequencies, which is what? Dike. I don't want to go into detail how frequency filtering is done because that's a geophysical feature probably. But petroleum engineers, they study a course called linear algebra and multivariable calculus. Am I right? You studied that one? And there is a part called Fourier analysis. Do you study Fourier analysis? Petroleum engineers. So in Fourier analysis, you can do frequency filtering and remove high from low frequencies. Another type of filtering is moving average. It moving average can remove high frequencies. So if you are interested on granite, you probably do moving average filters. Anyway, these are how the residual to regional, what the time is. So let's see how much slides, more slides left. Okay, 1, 2, 3, 4, 5, 6, 7. So let's complete this section. We'll do the lab next time. What do you say? Huh? Agree? I will change then the dates of the lab. They will get angry on me. So usually we talked about the response we get either from sphere and cylinder. It's hard actually to distinguish them easily because of what we call non-uniqueness. Many different models can give you the same response. That's very true in especially potential field methods. Gravity and magnetic methods, they are potential field methods. So it's actually hard to distinguish what created the response. There are millions of different models which can produce the same geophysical response, especially for gravity and magnetic, which is not quite true for non-potential methods. Resistivity model, usually you will get 1 or 2 models. It's very unique. Seismic, yeah, still you get 1 or 2 models, especially if you are trying to get only the image, amplitude sections. So how we determine probably the shape? Someone asked, how I can tell what kind of shape or what type of body I have? There are some basic rules. We'll discuss those rules. But first, let's discuss about how the survey is done, how we conduct survey. So we do survey basically establish first of all a base station and revisit the base stations. And gravity is very good in determining even oil fields where hydrocarbon accumulation are. Seismic performs really very poorly whenever there is, let's say these are, or let's make them straight, strata, and they got pierced. What could this be? Salt. That's a salt. So when the salts pierce to the strata, it deforms the layers. They become something like that. So the potential places to drill, the best place actually to drill here, you might have accumulation of hydrocarbon somewhere here because that's what we call an anticlinal four-way. It's closed from all directions, four-way deep closure. There are other places. That's where they target oil in Gulf of Mexico. You see these places? What do you think about the permeability of the salt? Very low, impermeable rock. So it can act as a seal, a cap rock. So if there is an accumulation, it can be, assuming that the rock here is also impermeable, seal rock. What's the problem with seismic? Seismic cannot, never ever, even if you do very advanced seismic, you cannot determine this boundary. You cannot tell where exactly is this boundary because of diffractions. A lot of diffractions happen here. You don't need to know, but the principle here, seismic cannot image salt domes. You cannot get anything inside the salt dome. Seismic image layers, strata, layering. If there is no layering, which is the salt dome, and for such complex features, seismic might not work perfect. So what could be helpful? Gravity. Why? Because salt Salt has very high density, 4,000 meters per second. But its density is low. It has low density compared to the strata for the salt. It's a good sign. So if you get an anomaly, something like that, oh, there could be a salt. Let's find what this X location is, and this X location exactly probably here. Let's drill here. You have already some idea because the seismic works away here. In here, at exactly where this area is, the image is not clear. The seismic section is not clear. Gravity works. Actually, there was an instructor here, a doctor. He joined PDU and he has been working on such projects. Non-seismic methods to identify especially areas of difficult geology or complex geology, similar to what we are discussing here, salt domes. That's one way. Another thing, in Oman, most of the fields in Oman are actually developed because of salt movement. There was a big salt in Oman. It's Ghaba Salt Basin. Have you heard of it? Fahoud Salt Basin and South Salt Basin. The three salt basins, it's almost one, but because in between them there is an exposure or an uplift which cut the salt to three different entities. They are controlling actually. For example, Qal'alam is a field like that. Something like that. It's very close to the surface. It's almost like 500 or 200 meters. Beneath it is a big salt. Deep beneath is a big fault. Very, very deeply seated. And in Oman, they call some places Qarat, Kibrit. You can go and touch the salt, get the salt. The salt pierced through all the layers, came to the surface. In all days, that was actually the source of salt for some people in Oman. Another place to get a lot of salt is, what is the country beneath us? Our neighbor? Yemen. Very clean, nice salt domes exposed to the surface. You go grab a big salt. In Oman, once these were deforming or getting created, they take a chunk of rock. They move, they might take a chunk of rock along with them, big chunk of rock. That big chunk, it's as big as like villages. That chunk is so big, it's as big as village. So there could be a chunk of rock moved along with the salt. They are very prolific. Why? What I mean by prolific, it means they contain a lot of hydrocarbon. Since it's inside salt, do you think seismic can help? Nope. Sometimes, in some fields, they are blindly drilling. And based on statistics, تعودوا كل ما نحفر 5 نحصل 1 successful. The rest are not. They get used to this habit. Oh, every time we drill 5, but not arbitrarily based on some statistic. Distance المفروض يكون كذا. ونعرف ان السولت حجمه كذا. تعال نحفر يمكن ما نحصل. And that's what they were doing. But if you do gravity, these are of higher density. What you will see, you see such features. What is that? An anomaly, small anomaly. This is the regional, this is another small regional, this is very specific thing where you can find it here. To find such features, if you drill them, you get a lot of hydrocarbon. Not all of them, but many of them, at least in the case. That's the case in south of Oman, in South Oman Salt Basin. And that, if you want to detect such small anomalies, we conduct a survey called microgravity. Microgravity is basically a gravity survey. The only difference is that, what do you think? What's your name? Huh? Ali? Ali, what do you think microgravity? What's the difference between aneogravity and microgravity? The resolution. How I can increase the resolution? Spatial resolution. How I can increase it? Huh? Huh? How I can make microgravity? Decrease the spacing between stations. Make them small stations. Instead of 15 meters, make them 5 meters. And PDU, they used a lot that. They used microgravity a lot to target such features. They were using microgravity. So this is a map. This is an eventual map. It's a map of what we call a map of what? Bouquet anomaly. That's a Bouquet anomaly. Things are not as someone's wishes. So here we have some empty area. Why is that? Because we couldn't cover or make a lot of points here. And that's a map. So we do model. After we finished correction, we start modeling gravity data. And as I said, modeling is not an easy task because specifically for gravity results, there could be many models that produce the same results, and that's referred to as non-uniqueness. So there are some complications. Here I have a data. Which one you think produced this anomaly? Is it this sheet? The middle one or the lowest one? Maybe all of them or anyone individually? Anyone individually. Use this one or this one or this one individually, they will produce the same results. Which one is true? Which one is correct? We don't know. We don't know. Huh? We need to drill, probably. We need to use another technique. Maybe magnetic, probably, it's cheap. We need, if we have seismic land somewhere close, it can give us some guess what could be true. So we need to bring other informations. We need to look for outcrops nearby. If there is any outcrop, geologists can help us with. Oh, do you think such feature is possible here or not? So you constrain, well, that's what we call constraining, yani. Decreasing the uncertainty within your models. So here I have again an anomaly. As I said, I gave you this example previously. These two models, they are different models, not big difference, but slightly there is a difference. They produce the same results. One way to consolidate, to remove the uncertainty is to drill. And when we do modeling in gravity, as we know, there is a forward model and inverse modeling. Forward modeling is moving from a model to data. The inverse is having data, trying to guess a model. And these two things work together. So if you have this data, original data, you start building a model, assign each layer a density, and you know how the gravity equation works. So what do you think if I made a measurement here, what kind of response I see? So if your response is similar to what you originally made in the field, it means your model is acceptable. That's one of the criteria we use in geophysical data analysis. So this is another kind of modeling. So this is a complication, as we see. These two models, they are producing same data. Here, either I have a surpass of density and increase in density in one side or decrease in the other side, I will receive the same, I get the same anomaly. I get the same anomaly. So again, to resolve, consult whom? Who is the guy who can help the geophysicist? Geologist. Consult the geologist. He might be better now, having better knowledge or aware of the geological things about the area, especially having knowledge about local geology. So we were talking how to determine basically some, if we are not doing modeling, if we are not using computer techniques. Oh, sorry. This is a computer technique. That's how we use computers. It's the best thing. It's advanced thing. But if this is a complex anomaly. However, if you have a simple anomaly, you can get some information about the shape of the body. And how is that? We use a rule called half depth rule. It's called what? Half depth rule. But how this works? This works again by making some guess. By making what? Guesses. You guess. I receive such an anomaly. How I calculate the depth to the body? What is the depth to the body? That's your anomaly. How I can give the depth to how much I dealt to reach that anomaly or the body that produced this anomaly. If you think it's a sphere, you use this rule. This will give the D. D gives you the distance to the center of the sphere. If you believe it's cylindrical feature, long cylindrical feature, use this rule. So, what is half depth? How I get the half depth? This value, these parameters. I get it from the anomaly itself. That's my anomaly. I try to find what is the highest value. Go to the midpoint, the average value. I reach the average value, draw a line up until the center of the anomaly. So the x-axis, what it represents? Huh? What is surface usually? Distance, yes, distance. One point, another point, a lot of measurement. That's the anomaly itself. That's illegal. So this here, that's the value here. Again, the same principle, but you only change what is this constant, this value here. It changes based on your guess, whether it's sphere, it's cylinder, it's another shape. So this is the cylinder. For the cylinder, it's simply the same value, The alpha value, or A, is 1. So dipping sheet, what could be a dipping sheet? A dike. Dike could be a dipping sheet. What could be a cylinder? A tunnel, maybe. A horizontal tunnel. What could be a sphere? A cavity, probably. You know what's a cavity? Or could be a gold mine. You assume it's or body, yes, that's what I say. Could be cylindrical shape. If it's very irregular and you have a nice anomaly, you think the shape is irregular, it's not any of these what you have, we're still using half depth rule. You first of all calculate the gradient. How to calculate the gradient of a curve? Yes. What is the that tangential line represents mathematically? Huh? Come on. How to get the gradient of a line or a curve? Gradient. You do either. What shall we do? Integration or differentiation? Differentiation, derivative of the curve. You do derive. Derivative of the curve gives you this value. Delta G over delta X. That's what we call derivative of the line. I believe you have studied derivative in calculus 1 probably or calculus 2. Calculus 2. Who has studied calculus 2? Many of you. All math, all engineers study calculus 2. So that's a derivative. The derivative of the line gives you the gradient of the line. Gradient of the line is the derivative of the line. So you get what is the maximum gradient. What is the gradient here? 0. What is the gradient here? 0. It increases. What is the gradient of vertical line? Huh? Infinite. It's error يعني. Yeah, it's not possible. What's the gradient of slopes horizontal line? 0. So the maximum gradient is in this deflection point. This deflection point. So that's where you get the maximum gradient. You differentiate it, try to find where is the maximum. That's how is it. Another way is to do derivative how many times? 2 times. You do derivative 2 times. And first derivatives gives you what? If I draw the derivative curve, max, small, max. Because again here becomes maximum. Or it could be, max here, assuming only the positive values. Again, I get another curve, derivative curve. What is the derivative of the second derivative? It's 0. That's clear. You know that. So anyway, we get the maximum derivative, maximum gradient. And we also need the maximum value of delta G. So the depth, not the center to the top of this body, could be anything smaller than this value, this constant, times what? Times the ratio of maximum divided by the gradient. Do you need to save it? Remember it or save it somewhere in your mind? No worries. So I think I exceeded my time. Let's see. We can keep this one for the next time. That's the last slide. Just to make things interesting. You are in hurry to leave? Got exhausted? Huh? The room is so hot. I'm already sweated all over. I need to have a shower. So stop the recording.